Hello, I'm Dr. David Kortowitz and welcome to Solidworks. Today we're going to be looking at how to use the built-in simulation tools to perform a finite element analysis of a part. This is very useful if you want to understand how a part will act under forces and other external loads in the real world. Let's begin. I've created a cafe table here using some cast aluminum 1060 alloy. And it looks pretty good, and we want to know how much weight it can handle. So first of all, we can look at the mass properties for it and understand that this table weighs about 40 pounds, which is a very reasonable amount, also translated to 18,232 grams. So what we want to do today is actually test it under an appropriate load. So the first thing we're going to do is go to our Solidworks add-ons tab. And if we go to the add-ins tab, we want to turn on Solidworks simulation. In my version of Solidworks, I have it set to automatically load simulation at the beginning. However, you may not have that configured at this time. If you do not, simply click on the Solidworks simulation and wait for the simulation tab to appear in your control manager. So we can click on the simulation tab and we can begin our finite element study. The first step here is going to be to save our document, giving it a name that's appropriate. So this is going to be table. And now once you have your the first step is going to be to go to the SolidWorks add-ons tab. The first step is going to be to go to the SolidWorks add-ins tab and click on SolidWorks simulation. Now, my version of Solidworks is set to automatically load simulation at runtime. However, yours may not be. If it is not, click on this button in the add-ins tab and look for a simulation tab to appear in your control manager. Go to the simulation tab and choose New Study to begin your new study. For today's study, we're going to be using static analysis, which basically means that the parts don't move. You can do other types of study here, but this is beyond the scope of this course. So we're going to choose our study and click OK. If you want to name it something other than static 1, you are welcome to do so, but we're going to begin it. So now we have what looks like the exact same thing. However, more things are available on our simulation toolbox. The things we have to worry about in this case are things like fixtures as well as loads. If we do not apply fixtures and loads, we won't actually be able to test what we're trying to test. Now, realize that if you don't put fixtures and you put loads, things are going to fly through space because they are not fixed in space. However, if we don't apply loads, we won't be able to test forces. So the first thing we're going to do is click on the down arrow for the fixtures tab and select fixed geometry. We have ability to put things like rollers and hinges and things like that, but hopefully this cafe table will be sitting stable on the ground. So we can choose, again, fixed geometry in our menu. And now we're going to come to the bottom here and we're going to select just the little edge that's going to be touching the ground. I'm going to click there. We're going to click on the edge over here that's touching the ground. And like that. And so we've selected just the edge that's touching the ground, and you'll notice that we get some green arrows along the edge. Now in this case, because this isn't perfectly round, we're going to have to go through and select the edges for each section. So we just go ahead and do that. So now that we've selected all the edges, we can click OK. These green arrows are telling us that that is a fixed geometry and will not move within space. Now we're going to put a load on the top of the table. To do this, we're going to go to the External Loads tab. I do not recommend using the advisors, so don't click on the buttons. If you do, it's just going to give you a help file on how to do what we're doing right now. But if we pull down, we can choose either a force or an external load, or pressure or torque. So let's pick a force, and we're going to click on the top of the table. Now, if you notice, this force is distributed evenly around the top. That is kind of by design. You can try other settings if you'd like them. So now what we have to do is figure out what we want to do. So we can set normal direction, or we can select angles if we'd like to. And we can choose whether we want to be in SI or English or whatever. But let's choose, for the time being, English, just because pounds seem to make more sense to Americans. Let's try a load of, say, someone sitting on the table. So 200 pounds. This is 200 pounds force, not pounds mass. But that is a finer detail here. Now that that force is set, we're going to click the OK button. Our study is now completely set up. However, we may want to make some adjustments to our study to see if we can get better results. Now that we've got all of the forces and fixtures applied to our model, we must create the mesh to solve. To do this, we can right-click on the mesh command and hit the Create Mesh button. When we do this, a menu comes up on the side. This menu has the ability to go from coarse to fine. This adjusts the size of the elements which are solved upon. The finer the mesh, the more detail you can see. However, it takes more computational ability to solve meshes that are finer. You don't want to make your mesh too fine if you don't need that level of detail, as it can cause crashes in computers with less memory and CPU power. The next thing we have here are our mesh parameters. Typically, this box is not checked. In your mesh parameters, you can say curvature-based meshes versus blended meshes versus standard meshes. In a standard mesh, you have pyramid-shaped elements, which are known as tetrahedra. A tetrahedral mesh represents most things well. However, it's been found in this table to not really work. So we're going to use a blended curvature-based mesh. When we click the check mark, a new window is going to pop up. This new window looks like this and gives us the information on the progress of our mesh. When it's complete, you may or may not get something like this that says that there are very high aspect ratios in the current meshes. It can compromise solution. Now, if you're doing very fine solutions, this actually really does matter. But in the case that we're testing today, we really don't care. High aspect ratio meshes mean that they are not close to isotropic, which means that you're going to lose detail in one or more directions. In this case, I'm going to say yes, that's okay, to show the plot. And so this is kind of what our mesh looks like. On the whole, things that are clear are perfectly good. Things that are in red tend to be things that are problems. So this means that the detail near the joints on the corners are going to be a little lower. Had I filleted this, this likely wouldn't have been a problem. That said, for the purposes of today, we're going to leave things as they are. So we're ready to run. So what we're going to do is we're going to say run this study and click on that, and a new window will pop open. I'm going to move this window in now. So what's going to happen is it's going to take some time, and it's going to solve the math required to solve our load. This can take a few minutes, and we will continue once this is complete. Our solution is now complete, and we are showing on the screen the results of the simulation. Now, one thing I want you to notice is that the table center has buckled quite a bit. The thing is, if we look at things, we're beyond our yield stress here, but we're not really showing what we think we're showing. Right now, we're showing our von Mises stresses. However, we would want to show in reality our displacement to understand what's going on. So with our displacement, we can just double click on it and it will change to displacement. Areas in red are going to be higher levels of displacement. Now, it's important to realize that the displacement that we're experiencing here is relatively small. It's somewhere on the order of 26 millimeters or 2 centimeters. However, in our image, it doesn't really tell the whole story. We don't see that this displacement is as little as it is. The reason being is Solidworks will over display the displacement in order to give you an idea of what it would look like if it failed. If we come in and right click on the displacement and hit edit definition, we will get a menu on the side, and if we notice, we're showing 4.5 times the deformation that's currently present. To fix this, all I'm going to do is hit True Scale. True Scale will repair our drawing or our model to show us exactly what's going on. So if I click OK, we now see that this is what's really going on. And in looking at this, we notice that the table really doesn't handle this load very well. So one thing we can do is go and revise our study slightly. So let's look at what happens if I put 100 pounds force. So we're going to edit the definition of the force, and we're going to change it to 100 pounds force. As the mesh is already built, we simply just need to run the study again to get a new set of results. So we're going to click there, and our study run box will come up, and you can hit the details to see what is going on. Again, this can take minutes. I've seen some studies take over hours, so be careful when you're doing larger studies, but we'll continue once this is complete. The results are in, and we can see now that we still have an area, anything above this green, that exceeds the yield strength, which means we will see deformation and possibly failure. But if we double click on displacement again, we can see that the displacement now is somewhere on the order of 13 millimeters, which is a lot less than what we had previously seen. It's still not ideal, but it's a little better, and you can see that the surface doesn't show major deformations. We have the ability to look at this in terms of not only displacement, but stress, which is the first level. And again, if we want to see what it really looks like, we have to go in and edit our definition and set our definition to True Scale, because it's showing everything with 9 times more deformation than it's actually there. We can set it like this. So what we can see if we look at the top, that there really isn't very, very high amounts of stress and strain except for around the boundaries. This is mainly due to displacement and to things moving. Now again, we can go over to our strain, and we can look at what our strain was. And again, we need to edit the definition and set it to True Scale to see what's really going on. So if we click on this, this is allowing us to see what the strain looks like. So our strain in our material is maximal around this ring again, slightly outside of the center. This is important to note because this is going to be the weak part of your table, and therefore could use some reinforcement were you to design this table. Now, if you're going to show multiple different drawings of things like this and multiple different models, make sure that your units stay the same in this bar. To change your units, you can simply just click in the bar and set what their values are. So we can say something like this is going to be, 1e-7 down here, and we can say that this is going to be somewhere around 10e-4, for example. And what that's going to do is that's going to allow us to be standardized across multiple drawings. So this is going to allow you to be standardized across multiple models and drawings so you can compare apples to apples. I've seen students before put in models that have different color bars, and it becomes really difficult to tell what the point is in terms of how different designs affect different parts. So in a nutshell, this is our finite element analysis tools within Solidworks. There are additional tools available, and you can use the tutorial system to learn about them. Thank you for your time today, and see you next time.